Our third example here, or question on our applications of quadratics, is talking about a rock being thrown from a cliff, and the rock is modeled, the height of the rock is modeled by the relationship that I've given to you here. And h is your height of the rock above the ground below the cliff, not in relationship to the cliff, but the actual ground below the cliff in meters, and t is your time in seconds since it was thrown. From what height above the ground below the cliff, so not above the cliff itself, was the rock thrown? So this has some implicit information given here. When the rock was thrown, we know something about the time at that moment. The moment that ball is, or that rock in this case, is released, the time equals 0. Okay, so at the point when we're really looking at the initial height of the rock. So time is 0, so we're going to actually solve for height by putting in 0 for time. So we've got 0 going into the equation where the t's are, replacing them with 0, whoops, plus 75 here, and 0 times anything will always equal 0. So this becomes a 0, this becomes 0. So this constant, that c value, is the y-intercept, or in this case the height intercept of the rock. So height is 75, so the rock was thrown from a height of 75 meters above the ground. That's a pretty tall cliff. So no factoring needed for that. We just had to use the equation we were given and interpret what we had. Now we want to express the relation in its fully factored form. So we're going to use the factoring tools that we have here. Always, always, always look for a common factor first. And because my a value in the equation, the a value is a negative, I want to definitely factor the negative out, if nothing else. But I'm also noticing I can easily divide 10 and 75 by 5. So I'm going to common factor negative 5 out. It's going to leave me with a t squared. Negative 10 divided by, or positive 10 divided by negative 5 will give me negative 2 with a t. And positive 75 divided by negative 5 will give me negative 15. Now what I'm left with in that bracket is a nice little trinomial, and it's simple because I have a 1 in front. I want to find two numbers that are going to add to negative 2 and multiply to negative 15. So 1 times 15 multiplies to 15. 2 doesn't go in evenly, but 3 does. 3 times 5. I want to multiply to a negative, and I'm adding to a negative. So my larger numbers have to be the negatives. And I made a little oops there. There we go. And so I think this combination right here will work because positive 3 take away 5 is negative 2. So because it's a simple one, we can go directly to that factored form of t plus 3. So we're just using these numbers exactly as they are. So t plus 3 times t minus 5. Hopefully you can tell the difference between my t's and my plus signs here. All right, so that's good because we know factored form tells us something. The factored form will tell us the zeros for our parabola. So my zeros here, remember switch the sign, are going to be negative 3 and positive 5. Okay, so that gives us our x-intercepts of negative 3, 0, and positive 5, 0, or in this case our t-intercepts. So if we think of our graph of that relationship, we have a negative 3. Let me just extend this a little bit. So we've got our negative 3 and our positive 5, and the parabola is opening down because our a value is negative. We have something that looks like this. So this is our time axis, this is our height. Here's the negative 3. And here's our positive 5. This value right here on the h-axis was that 75. It's the initial height of that ball. So it takes the ball 5 seconds to hit the ground below the cliff because the ball goes up in the air and then comes back down, and then the height is 0 at 5 seconds. And I know I keep saying ball because it could be a ball. It could, in this case, I wrote the word rock, but sometimes we use balls being thrown off cliffs or roofs of buildings or whatever it happens to be. All right, what time does the rock reach its maximum height here? Again, we can use symmetry with this. Now, in context, we wouldn't actually have time being negative 3. We wouldn't be going back in time. But for the parabola itself, we are looking at that -3 to find that axis of symmetry, that time that's going to be halfway in between. So again, we want to add those two values together, -3 plus 5, and then divide by 2. We're finding the midpoint. So that gives me 2 divided by 2, which is 1. So it reaches the maximum height 1 second after it is thrown. All right, and at this point now we want to find the actual maximum height. So again, we know it reaches the maximum height at 1 second. So we're going to sub in t equals 1 into the equation. So into equation. So we're going to go back to the equation because it tells us the height is really just going to be whatever you get when you take -5. I'm using the wrong number here. -5 t squared, and I could use the factored form, or I can use the original, what we call the standard form, to sub that value in. It doesn't matter which one you use, either one should work. Oh good, this worked this time. Equals -5 times 1 squared, which will just be -5, plus 10 times 1, which will be 10, plus 75. We know the answer should be bigger than 75 because it started at a height of 75. That's going to be adding 5, that's going to be 80. All right, so the maximum height of the rock is 80 meters above the ground. And then we have expressed the relation in its vertex form. So again, that vertex form, we want that value of a to be -5 because that's what it is equal to in the original function. So y, or no, I'm going to use h for height, equals -5, bracket, t for time, t, and then we had it happening, the maximum was at 1, so it's t minus 1, all to the exponent of 2, and then plus 80. So now we've written that relationship in all three forms. We have the standard form, we have the factored form from part B, and now we have the vertex form. All right. One other thing I want to talk about here is the values that t can take on. For the actual parabola, without the story, if I just wanted to know what the domain or the values that t could take, it would be all real numbers. But because we have a story for this parabola, we have context for it, and we're talking about time, time does not make sense to be negative. So time starts at 0, and the parabola makes sense until that rock hits the ground. It doesn't just keep plummeting into the earth and burrowing a hole into it until it gets to the center of the earth and dissolves into molten lava. Our context for this then is just the values of time between 0 and 5. So if I ask you what values would make sense for this particular context or story, our time values make sense between 0 and up to and including 5. So I could write that as 0 is less than or equal to t, it's smaller than or whatever equal to whatever t can take on, and t has to stay less than or equal to 5 in this case. And t is any real number. You can have decimals and fractions and whole numbers, any value between there works. All right, our last example here. A rectangle has this area. Determine an algebraic expressions for the length and the width of the rectangle. So a rectangle has an area of length times width. So if I just draw a picture here, we know a rectangle is length times width. So that means if my area, the area is given by this expression of 2x squared plus 5x minus 12, and we want to get expressions for the length and the width, we want to rewrite this as something times something. Now, this is 3 terms. First thing I want to look for is a common factor. I don't see anything that I can divide every single term by evenly, nor does every term have an x. It's also not going to be a simple trinomial because I don't have that 1 there. So we're going to be looking for 2 numbers that add, it's a tricky trinomial, that add to positive 5 and multiplies to negative 24. Remember, we get that negative 24 by taking the negative 12 times the positive 2, the a times the c. So let's see if we can come up with some numbers for that. 1 times 24 multiplies to 24, 2 times 12, 3 times 8. It's helpful if you know your number facts. 4 times 6. Oh, wait a second. I also have to have a negative answer. So 1 is positive, 1's negative. And because I'm adding to a positive, the positives have to be the larger numbers, and I think this combination will add to positive 5. I can't go directly to my factored form, so I'm going to get my little eraser here and erase this. All right, so let's use the decomposition here. I'm going to go 2x squared. I think I'm going to put the 8 with the 2, so I'll go plus 8x, and then I'll put my minus 3x, and then minus 12. And then we pair them up for that common factor. In the first pair, that has a common 2x. So I'm going to common factor 2x out of both of those, and that gives me x plus 4. And then out of the second pair, I'm going to take out a minus along with the 3. And that's going to give me my positive x. And then minus 12 divided by minus 3 is positive 4. That's good because these two brackets have to be the same in order to make this work. X plus 4 is now our common factor for that, and 2x and minus 3 is what you have left after you divide both those terms by x plus 4. So we could say the length, and it doesn't matter which one's which, the length is x plus 4, and the width could be the other one of 2x minus 3. And there we have it, expressions for the length and the width.